Okay, let's try this one. We're on the last one now, exercise 6 in paper 2. The following diagram shows a circle with center O and a radius of 1 centimeter. Okay, so we know there's a radius of 1. Points A and B lie in the circumference of the circle. Okay, so on the edge, and AOB is equal to 2 theta. So we've got our angle here of 2 theta. And we know that theta is supposed to be between pi half and 0. Okay, and in a sense that this means that our 2 theta must be able to go from 0 and up to pi, because it's twice as big, right? So, okay, that makes sense. Now, it tells us here the tangents to the circle intersect at point C. Okay, before we go any further, I want to point something out, something very important. Do you see how it uses here? It shows here these clear little 90-degree markers. I'm going to make them a little bit clearer still, because I really want to emphasize that this means that we're going to use this information in the problem. They don't provide this kind of information for fun. Whenever you see that there is a 90-degree angle and they've clearly specified it like they have here, it means you're probably going to have to use that. Keep that in mind, because it's a useful tool for finding the clues to solve a problem. So the first question they ask is, show that AC is equal to tan theta. Okay, let's think about this problem for a moment. Let's start with the most simple aspect here, theta. If we look at this, we don't see just a regular theta, we only see 2 theta. How can we get regular old theta to appear? Well, what if we were to say, draw a line from here out to here? Then I'm hoping that it's clear that you would get a theta here. I'm going to have to draw this a little thinly. And you would also have a theta here, because we have very carefully sliced this in exact halves. These two triangles here, the top one and the bottom one, they are exactly the same. OAC and OBC, they are the same triangle, just flipped. So, okay, that can be our starting point. What should our next point be? We should probably think about where tangent comes from and how you can get it. If we remember our sine and cosine and such, we can remember that each one of these comes out of this idea for a right angle triangle anyway, which this is, so it's okay for us to use that. Then maybe you guys remember opposite over adjacent for tangent. So that means that if we take tangent to this, tangent of that, so if I have, I'm going to write it in red now to show that's important. So if I have tan of theta, then that should be the same as the opposite. What's the opposite to this theta here? It must be this side here, AC. So I should be putting AC up here. And then it tells me divide by the adjacent. What is the adjacent? Well, if this was the opposite, this side here is clearly the longest. This must be the, this one over here, this 1, that must be the adjacent. So I can divide by 1. That pretty much covers this part of the question, because now it's hopefully easy to see that that 1 should disappear, and you'll just have tan theta equals to AC. Once you have that, you're basically done, because it's like, oh, but this is exactly what we wanted to show. So we're through. The proof is basically going, remember that these are right angle triangles, remember that you could split it in 2, remember that it works like this, use your tan theta, see that the 1 disappears, and you get the result. Okay, let's take the next one. Find the value of theta when the area of the shaded region is equal to the area of sector OADB. So first off, let's talk about sector. Sector, you can get the area with the formula that is in the formula booklet. It looks like this. The only thing to remember is this is only possible in radians. So we need to remember to switch the calculator to radians when we do this problem. But that's okay. As long as we remember it, it should be fine. Next point. So sector, that's one thing. But what about this triangle? What about this shaded area? How do we get it? It kind of looks like, let me try and illustrate here with blue. It kind of looks like it's this triangle, for example, minus this sector, as if we just took this part away. But we already have an area. We already have an area formula for sectors, so that would just be 1/2 pi. This theta, again with an r squared, and it's the same r, so that's fine. And then we simply have to go, okay, that right there, that should be something that we subtract from the area of the triangle itself. And the triangle here, well, think about it. This side here and this side here form a right angle triangle. This is 1, and BC must be the exact same length as AC because they are the same triangle. So we could say 1/2, oops, yeah, 1/2 times, and then we could have in here 1 times AC, and then simply subtract this. Now here is the thing. What is our radius for the sector? Why, it's just 1. So I'm going to remove this r, and I'm going to fill in a 1 instead. Multiplied by 1, multiplied by 1. And then we think to ourselves, why don't we just use this theta here? Because here's the thing. This part here, if we focus exclusively, I'm going to shade with blue now, if we focus exclusively on this lower part, that's everything accounted for. We've got the sector, and we've also got the triangle minus the sector. We're going to see when those two are of equal size. If those two are of equal size, it must also follow that they're equal for the upper side as well. Like this up here, this one that I could draw in blue, it's exactly the same thing as the bottom one. So I don't have to account for both cases. I can just focus on one triangle at a time, and then 1/2 of this problem at a time. So now all I've got to do is write up my equation. I'm going to go ahead and write in 1/2 theta times, I'm not going to write the 1 squared actually, because what is it if we have 1 squared? It's 1 times 1. That's the same as doing nothing, really. Then on the other side, I'm going to have 1/2, then times, I'm not going to have the 1, I'm just going to go straight to AC. But what's AC equal to? It's equal to tangent of the theta. So all I need to do is put in tan theta over here, like so. And then I need to subtract 1/2 times theta. Now, how do I solve this? How do I solve this? Well, what paper are we on? We're on paper 2. Whenever you see a complicated looking equation on paper 2, whenever you get to a point where you have a complicated looking equation, do not forget to use the GDC. I urge you to please, 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 please use the GDC whenever possible. So I'm going to quickly type this into the calculator, and with the moment I have it ready, I will show you exactly how it looks. I'm going to use the graphing function. Now, the reason I'm going to use the graphing function is because, in principle, there might be multiple solutions. However, or rather, actually, come think of it, there are multiple solutions. But some of them are more interesting than others. Because here's what it looks like when we do this problem. It kind of looks like there's an intersection here at 0 theta. But is that what we want? No. We aren't allowed to have theta be equal to 0. We already told us that. We already told ourselves that in the start of the question. So this is obviously out. The other thing, the other solution is over here, though, a little bit below 1.5. And here's the thing. Are we allowed to use this solution? Let's have a look. It can go up to pi divided by 2. Pi is about 3, a little over 3. So if we have something that's a little bit over 3 and we divide it by 2, that's a little bit over 1.5. This is below 1.5. So this is probably a fine solution, but it's the one that we want. If we had used nsolve, I'm going to write this down here. If we used nsolve, we would need to set bounds to not get 0. because otherwise NSolve would go, oh, I found the solution, it's here. And we'd be like, well, no, no, this is too small. And NSolve would struggle to get it right. I'll show you how you can do it if you really want to. The way that you can do it is very simple. All you have to do is, I'm just going to write up the question as it is, and then I'm going to explain what you do. So what I've done here is, I've solved it using NSolve, but what I had to do was I had to include what we call a lower boundary. The first thing that you put in is going to be the lower boundary. Basically, NSolve will not check below this. And sometimes that's useful, but again, you have to know not to look for that solution. With the graphing thing, it becomes very obvious where the second solution is going to appear, and you know exactly where it is, and you can just find it. In any event, though, the answer that I get, let me take a picture of it, is this. This right here is apparently the radians that you need. So I get that theta should be equal to 1.17. Let's not make it 6, let's make it 7, because remember, 3 significant figures. 3SF means round up. So we have our answer. And again, the trick was to remember that the calculator is our friend and it will help us. With that, that's paper 1 and that's paper 2. I hope this has been useful. And again, as I said, if you're ever in doubt about anything in any one of my explanations, or anything seems unclear or difficult to process to you, don't hesitate to let me know. I'm happy to try to answer any questions you might have about my walkthrough here. I've also uploaded all of the little of the pictures that go with this. Even if they're very ugly and hard to read sometimes, maybe it'll make it easier to follow along if you can actually read this more at your own pace. I hope that it helps.